Hi students, welcome to Govidya. Sorry for delay, some technical glitch happened, so we are not able to share the screen. Now I think it's okay. Good morning, welcome to the session. Today we are going to solve some questions related to induction machines. Most of the students are feeling difficulty in induction machines if the problems coming in on induction machines. Okay, so how to solve the questions from if the question is from induction machine? We need to first remember the basics. That means what is mean by slip, what is mean by torque equations, starting torque, maximum torque, and relational to maximum torque, like that, and starting methods of induction machines, like that. If you see some little basics, if you know, then it is very easy to solve the questions. Okay, so I will try to explain the concept with the questions at most. Okay, as time is very less for us, so I will try to explain the concept also along with the questions. If you have any doubt, we can chat over the comment box, we'll discuss there. Okay, let's start the session. The question is given about an induction motor has a starting torque of 320 Newton meter when started by direct switching. If starting through an auto transformer 50% tapping, the starting torque will be. Okay, so we'll note down about what is the concept behind the question. Concept behind is auto transformer starting. Okay, let's note down the given data. What is the given data? The given data is the starting torque when you are using DOL method. Direct starting means direct online starter, or DOL method we used to tell. So is given as 320 Newton meter. 320 Newton meter they given. So what we need to find out? Starting torque at the rate of auto transformer starting method we need to find out. First of all, I will give you one simple equation to remember. Any question related to starting we can solve with this equation. Okay, just remember this equation. The full load torque can be given as full load torque is directly proportional to rotor input. Okay, rotor mechanical input, that will be 3I square full load R2 dash divided by SFL. Okay, this is the rotor input to the rotor input. Okay, from this what you can write, that full load torque is directly proportional to IFL square and inversely proportional to SFL. Okay, let's write down the equation as starting torque to full load torque equal to I starting divided by I full load whole square into SFL by S starting. Slip, where S is the slip. We know that at the time of starting S is equal to 1. How S equal 1 came? At the time of starting NR equal to 0. So from this S is equal to 1. So our equation will be T starting to T full load equal to I starting divided by I full load whole square into slip at full load. This is the equation we need to remember. Okay, nothing to remember. I just given one equation here. The full load torque is going to directly proportional to the rotor input. If we are remember just this formula, we can derive our starting torque equation from that equation. Okay, from that formula. Once if you remember up to this, you can solve any question related to the starting of induction motor. Okay. So if you, here what we need to see, most of the times what starting current only we need to calculate. Okay, starting current. So we know that when at the time of starting rotor speed is 0 and slip is 1, and it leads to high starting current will be very high. By using different methods of starting, we are going to reduce the starting current. One of those method is auto transformer method. What auto transformer method is to, it is going to reduce the starting current by x percentage. Okay, in auto transformer method, the starting current can be reduced to x, where x is the percentage tapping. Okay, so let's substitute in this equation 1. From equation 1 we get that T starting to T full load equal to x I start divided by I full load whole square into SFL. This can be written as x square into I starting divided by IFL whole square into SFL. Okay. This whole term can be written as x square into T starting divided by T full load at the rate DFL, at the rate DYL. Okay, at the rate DYL. Okay, this is given as, this term can be written as starting by full load torque at the rate DYL. Okay, so therefore what you can write from this, therefore starting torque at the rate auto transformer is equal to x square into starting torque at the rate DYL. Okay, this is the equation we got from this. Okay, so where x is percentage tapping of auto transformer. So let's see the given data. I think percentage tapping also they given. The percentage tapping x is equal to 50%, that means 0.5 you can write. Okay, 0.5. Let's substitute that data in this equation. What we will get? Therefore starting torque at auto transformer equal to, where x is 0.5 whole square, and they given starting torque at DYL. What is that formula given? 320. It will be 0.25 into 320. We can write 0.25 as 1 by 4 into 320. From this we will get 80 Newton meter. Therefore starting torque at the rate of auto transformer method is given as 80 Newton meter. This is our answer. Is it clear? Okay, so if you remember the basic formula, from that we derived the equations. Our option will be B. Let's move on to the next question. The next question is given about torque and current are the current respectively. Okay, T and I are the line current and torque respectively when dual starter is used. These quantities when star delta starter is used. Okay, star delta starter. Let's note down the concept. What is the concept behind this question? They are asking about star delta method of starting of induction motor. Okay, so what is the given data? Given data is given as the current they given, line current IL, and starting torque T. Okay, starting torque T they given. Okay, so first we'll see what is mean by star delta starter. If star delta starter, just simple network, if you draw, if it is a star network, how it will behave. Okay, how it will behave. Let's take this is the Z01 and this is the line current IL. This is the phase voltage. Okay, in star network what will happen? That phase voltage is equal to VL by root 3. Okay, and this is the in IL is equal to I phase in star network. Therefore IL is equal to what you can write, V phase by Z01. It can be written as VL by root 3 Z01. Okay. If we are using initially star connection, the current formula will be like this. Let's see the delta connection. If you keep the induction transformer, the transformer connection in delta, how the current will be, we'll calculate. In delta connection method, how the voltage and current parameters are related, we will calculate. Let's take it is Z01. In delta, line current is equal to root 3 into phase current, and line voltage is equal to the phase voltage. From this we can calculate IL is equal to root 3 into I phase. What is the phase current? VL by Z01. Let's take it is IL delta, let's take it is IL star. Therefore IL star divided by IL delta equal to how much it will come? VL by root 3 Z01 divided by root 3 into VL by Z01. Okay, from this how much it will come? It will come around 1 by 3. Okay, it will come around 1 by 3. Therefore IL current is equal to IL star current equal to 1 by 3 into IL delta current. Okay, IL star current equal to IL delta current. See, in general induction machine is connected in delta connection. Okay, but if you see the current equations, if induction machine is in delta connection, it is drawing more current. To reduce that starting current, what we did, we connected initially in star and the current is reduced for some time. After reaching the speed 80%, again we will convert to delta. Okay, again we will convert to delta. So in a given question, they are asking about the how the torque and current are going to be in star delta transformer. So here if you see, this is going to be 1 by 3 times. Okay, 1 by 3 times of the delta connection. So let's see the options. Our options matching is only D. Okay, with just one calculation we came to know that our option is D. If required, you can do the torque also. We know that in star delta transformer, that starting current to full load current equal to 1 by 3 times of I starting by I full load whole square into SFL. From this you can write the torque is going to be, starting torque is going to be the 1 by 3 times of this, you can write it as full load current. Okay, starting current is going to be 1 by 3 times of full load torque. So our option will be D. Is it clear? If you have any doubt, please chat over the comment box. We'll discuss the concept again. Hope it is clear for all. We'll going to the next question. The next question is given as a universal motor is one which, okay, so what is mean by universal motor? Okay, what is mean by universal motor? In our theory concept you might have studied, universal motor is nothing but the motor can operate for both AC and DC. Okay, both AC and DC. In general it is a DC series motor. In general it is a DC series motor with some modification in construction. With DC series motor with some modification in construction. Okay, universal motor is nothing but a one of the DC series motor only, but little modifications done in winding and all, okay, to operate in AC condition also. Okay, this motor is called universal motor. Universal motor is nothing but we can operate this motor with either AC supply or DC supply. Okay, so our option will be C. Where we are going to use the universal motor? In our mixers and grinders. That means where high starting torque is required. Where we need high starting torque, and we can use for both AC and DC supplies. That type of applications we are going to use universal motor. One of those application is in our mixer and grinder. Is it clear? Okay, let's move on to the next question. The next question is about the power factor of induction motor at no load condition is. First of all, we need to understand how the power is transferring. Okay, how the power is transferring in induction motor. Let's see, this is a stator. Stator we are giving 3-phase supply. Okay, this is the rotor. Okay, this is rotor and this is stator. If you give the 3-phase supply, then rotating magnetic flux pi will generate and it will induce the EMF in rotor, thereby one rotor flux will create, and with this rotor flux and stator flux with the help of these two, one mechanism will develop, thereby motor will start rotating. If you see here, whatever electrical supply we are giving to the stator, this is not directly transferring to the rotor. In between air gap is there. Okay, this is air gap. Whenever air gap is more, the I mu will be very high. I mu will be very high. If I mu is high, cos pi naught, that means at no load condition cos pi naught is very less. In transformers we already seen how the relation between I mu and cos pi naught. Induction machine is nothing but it is a rotating transformer. All properties of transformers are applicable for induction machine also. And cos pi naught here is a lagging. Let's see the given options. Okay, so for lagging power factor they given 3 options. 0.8 not at all possible, 0.5 may be possible, but see, they are telling at no load condition. No load condition means power factors will be very less. It will be in the range of 0.2 to 0.3 only. So our option will be B. Okay, our option will be B. So this type of questions we need to come from the concept. Okay, is it clear? Let's move on to the next question. The next question is given as the value of slip of 3-phase induction motor at nth harmonic approximately. Okay, so we know that this ns is equal to 120 f by p. Okay, when this harmonics are coming, nth frequency will be nf. From there ns is equal to n into ns. Okay, so the slip slip S is given as ns minus nr by ns. Okay, so when harmonics are increasing means ns will get increase. Okay, ns is getting increases. So that time what will happen, ns minus nr is nearly equal to the ns for a higher harmonics, therefore Sn will be given as n into Sn will be given as n into ns by n into ns. Therefore slip at nth harmonic nearly equal to the 1 nearly equal to 1. Why? Because the synchronous speed is directly proportional to the frequency. If harmonics are getting increasing, so our speed, synchronous speed also will get increase, but the factor ns minus nr is going to be reduced, so it is nearly about ns only. Okay, so our option will be A. Is it clear? Let's move on to the next question. The next question is about in V by F control of three-phase induction motor, when it is operated at above rated speed, then. Okay, so they are telling the concept is about V by F control and above rated speed. So for this condition we need to understand what are the different points. Okay, for above rated speed V is going to maintain as V rated and frequency is going to be changed. Okay, we know that slip is inversely proportional to frequency. If frequency is increasing, slip will decrease, and if slip is decreasing, n are going to be increased. So the motor is going to be operated at above rated speed. So first thing what we need to understand, V is going to be maintained V rated, that means almost constant. Okay, only frequency is going to be varied in above rated speed condition. Okay, is it clear? Next, we know that mechanical power transfer is given as 2 pi nt by 60. Okay, from this equation we can draw the graph between speed versus torque and power, how it is responding. Okay, torque and power, how it is responding. Okay, this is the torque curve, this is power curve. This point is n rated. Above rated condition, this is n above, that means nr is greater than n rated. This condition they are asking. Okay, above rated condition, how power and torque is going to be increased. Okay, see, in the above rated condition, if you observe the curve, P is going to be constant and torque is reducing. These points we need to note down here. Okay, one more parameter they are asking is slip speed. Slip speed is nothing but ns minus nr. Slip is different, slip speed is different. These terms we need to understand. Okay, slip speed ns minus nr. Okay, so this is going to be, what is going to happen, if nr is increasing, slip speed is going to be increased. Okay, slip speed is going to be increased. Okay, this is the term we need to note down. Okay, we will come to the conclusion. They given 4 statements. Let's see what and all correct. Voltage decreases. No, this statement may not be true. Why? Because we are going to maintain voltage as rated voltage condition under V by F control when we are operating above rated speed. Okay, when you are operating above rated speed. First statement is not correct. Second statement, torque decreases. From this curve we can see above rated condition torque is going to be reduced. Yes, this may be true. Power increases. No, if above rated speed, if you see the curve, when speed is above rated speed, the power is going to be constant. This also not true. slip speed increases. Yes, slip speed is going to be increased. So only 2 and 4 are correct. Let's see the which option is suitable for our question. 2 and 4 are correct are only option A. Okay. Is it clear? Let's move on to the next question. The next question is about the slip of a 3-phase induction motor is 0.05. At the instant of dynamic braking, the slip is, okay. So the concept is about dynamic braking. Dynamic braking. What is going to happen in dynamic braking? In dynamic braking, induction motor will act as induction generator. Okay, induction motor will act as induction generator. We know that for induction generator the slip will be 2 minus S. Okay, 2 minus SF we can say. So the given SF is 0.05. So 2 minus 0.05 will be 1.95. Okay, therefore SG is given by 1.95. Our option will be C. Okay, it is simple question. In dynamic braking condition, the motor will act as a generator. Okay, the rotor speed will be higher than the synchronous speed. Okay, thereby it will act as a induction generator. For induction generator, the slip will going to be S is equal to 2 minus SF. From there you can calculate the slip. Our option will be C. Let's move on to the next question. The next question is about if an induction motor with certain ratio of rotor to stator slots runs at the 1/7th of the normal rated speed. The motor is said to be okay. Let's see the concept. Whenever this 1/7th speed is coming, in our question, it is related to the crawling. How? What is meant by crawling? Crawling is nothing but the stable operation of an induction machine. Induction machine at 1/7th of rated speed, 1/7th of rotor speed due to harmonics. Okay, what will happen in crawling? Whenever the motor is running at rated speed NR, because of some stator teeth harmonics or some other harmonics, thus frequency is going to be changed, thereby that signal speed is going to be altered. Okay, thereby signal speed is going to be altered, NR is also going to be altered, and the speed will come to 1/7th of rated speed, and it will continue in that speed only. It won't increase, the speed won't increase. That state of operation is called crawling. That means if the induction motor is fall down to 1/7th of its rated speed and it is not able to increase their speed and it is continuously running at 1/7th of rated speed with stable operation, then that state of operation is called crawling. Okay, so our option will be B. Is it clear? Let's move on to the next question. The next question is about the starting torque of induction motor is maximum when. Okay, they are asking the starting torque of induction motor is maximum when. So we know that maximum torque is equal to, at the rate of maximum torque we can say Sm is equal to R2 by X2. Okay, at the maximum torque, slip Sm is equal to R2 by X2. Okay, so at the time of starting, what is going to happen? At the time of starting, rotor speed Nr is equal to 0. So slip is going to be 1. Okay, slip is going to be 1. So from equation 1, from equation what we will write, R2 equal to x2. From equation 1, R2 equal to x2. So this is the condition for maximum starting torque. Okay, so let's see the options. Our suitable option is D, rotor resistance equal to the rotor reactance. Okay, is it clear? Just I taken the condition of maximum torque, that means at maximum torque slip is going to be equal to the R2 by x2. From that I substituted my starting condition, thereby I got the condition for maximum torque at time of starting. Is it clear? Let's move on to the next question. The next question is given about a 400 volt 50 Hz 3-phase induction motor rotates at 1440 rpm on full load condition. The motor is wound for. Okay, so this is just somewhat typical questions, but we need to go for some assumption also. Okay, let's note down the given data first. The frequency is given as 50 Hz and NR is given as around 1440 rpm. What they are asking? Number of poles. We know that synchronous speed ns is equal to 120 f by p. Okay, if you know the synchronous speed, then you can calculate the number of poles. But in the given question, the data is about rotor speed. We know that the synchronous rotor speed is near about to the synchronous speed. Okay, near about to the synchronous speed. Now we have to take some assumption. The nearby round figure is 1500. So we need to assume ns is as 1500 rpm. If you substitute 1500 rpm here, 120 into 50 divided by p, we have to calculate the p. Three ones, 3 fours. Okay, therefore p is equal to 4. So number of poles will be 4. The option will be B. Okay, sometimes we need to assume some data. Okay, we know that that the synchronous speed is near about rotor speed, so we are taken a near round figure. 1440 they given rotor speed, so the near figure is ns is 1500 rpm we considered. From that we calculated the number of poles. Is it clear? Okay, let's move on to the next question. The next question is given as the slip of 400 volt 3-phase 4-pole induction motor when rotating at 1440 rpm. Okay, so this is also similar to the previous question. They given as poles, poles p is equal to 4 they given, nr they given as 1440. Okay, nr they given as 1440. So in general frequency will be 50 Hz. Okay, in general if they not given, we have to consider it as 50 Hz. Okay, therefore we can calculate ns is equal to 120 into f by p. 120 into f is 50 Hz, p is 4. From this we can get ns as 1500 rpm. What is the formula for slip? Slip is given as ns minus nr by ns. What we got ns from the calculation 1500. The given data for nr is 1440. Okay, ns is 1500. 60 divided by 1500. How much it will come? Let's do the calculation. Approximate is also fine. It will be around 0.04, but they are asking in percentage, so we need to multiply the 100. Percentage will be 0.04 into 100. Therefore percentage slip is equal to 4%. Option is C. Is it clear? Let's move on to the next question. The next question is given as torque developed by 3-phase 400 volt induction motor is 100 Newton meter. Okay. If the applied voltage is reduced to 200 volt, the developed torque will be. So, if you read out the question, the concept is about speed control by controlling the voltage. We know that the relation between torque and voltage. Torque is directly proportional to the V square. Okay, torque is directly proportional to the V square. Let's note down the given data. What is the given data? Torque T1 given as 100 Newton meter, V1 given as 400 volts, V2 is given as 200 volt. We need to calculate T2. Okay. Therefore, T2 by T1 is equal to, from equation 1, let's take it as equation 1, V2 square by V1 square. So, T2 equal to, what is V2? 200 divided by 400 whole square into, what is T1 given as 100? 1 by 2. That means 100 by 4. Okay. Therefore, T2 is equal to 25 Newton meter. T2 is equal to 25 Newton meter. Our option will be B. Is it clear? Okay. So, what they given in question? The question they given torque at certain voltage they given. Now the voltage is reduced. What about the torque? So we know the relation between torque and applied voltage as T is directly proportional to V square. From that we calculated the torque for required voltage. Is it clear? Okay. By this we are going to wind up the today's session. We will continue some more questions related to induction machines in the upcoming classes. If you have any doubt, please shout out the comment box, and we displayed our contact number. You can contact us. We are going to provide guidance for your preparation also. So my sincere advice for preparation of induction machine is, be clear about the basic concepts. Okay, if you are clear about your basic concepts, then you can solve any questions from the induction machine. Why? Because I saw many students, they are struggling while solving the questions in induction machines. So the questions may be little twisted. That means they will twist somewhere the data. But if you are clear at basics and you write down from the step by step what is the given data, you can solve the questions easily. Okay. We will solve some more questions. So I will try to explain the concept through the questions as much as possible. Okay. If you still have any doubt, we can contact that number displayed there, and we can put a comment in the comment box. We'll get back to you. Thank you. By this today's session we are going to complete. Tomorrow we are going to continue for induction machines only, sharp by 6 o'clock. So please share the link to your friends so that they will also get benefited from this session. Okay, it will be helpful for the